partial derivative with respect to the time, then you only differentiate the field with respect to the time and not with respect to the position vector. Now we have also here this nabla operator, which is such a triangle. And actually this nabla operator is a vector that consists out of these partial derivatives with respect to x, y, and z. So it's basically, it condenses all of the spatial derivatives. So what we can do now is we can start from this Maxwell equation here, and we can just multiply this nabla operator from the left with such a vector product. So this rotation of the electric field is this term here. So here again we have to put nabla cross to the left. And now we can just switch around these two derivatives. So we can write minus partial derivative of time of the rotation of B. Now what is the rotation of B? It's of course this one. So we will have now the time derivative of this term and the minus sign. So we will get minus these two constants, and then here, now we have a second derivative of the electric field with respect to time. And as it turns out, these two constants are actually directly related to the velocity of light. So you will soon realize why I'm doing this calculation. What we have now here is some rotations of the electric field, and here we have the second derivative with respect to time. Now we can now use properties of such an expression where we have a double vector product of the nabla operator to such a vector, and we can use a vector identity. So for every vector, it doesn't have to be E, it can be any vector, this relation is true. And now we can look at this term. We have now the divergence of E, which is 0. So this whole term here is 0, and we end up with this term being the Laplace operator applied to the electric field. So this means this term is equal to this term, so we can end up with such a differential equation. And this is actually the wave equation. It's the differential equation in the vacuum that gives rise to light as an electromagnetic wave. So just again a heads up if you don't know this opposite triangle is called the Laplace operator, and it's the sum over the second derivatives with respect to x, y, and z. So as you may have noticed, I have already here introduced some mathematical concepts that you are maybe not familiar with if you have just finished college, for example. You probably know what a derivative is and what a second order derivative is, but you don't really know what a partial derivative is. But it's quite simple, here you can see it. But still, some of these concepts, for example the nabla operator or the Laplace operator, may be quite new for you. So if you are confused by this, then don't worry, I have you covered. So I have included in this course a 2-hour section of a mathematical tutorial on all of the mathematics that we will use throughout this course. So I don't really want you to just go ahead and watch the tutorial. I basically want you to continue with the course and see if you get along with it or not. And then at some point we will get to the tutorial, and then you can decide if you want to watch it or if it's all fine for you and if you manage to do it without the tutorial. Okay, so now let's go back to the topic. We have derived here this wave equation for the electric field in a vacuum. And now let's sit together and guess the solution. So what we must have here is that the second order time derivative of the electric field must be somewhat equal to the second order space derivative of the electric field. So a possibility would be to consider just a cosine function. Because when we calculate the derivative of the cosine, we get minus sine and then the inner derivative. And then if we differentiate once again, we get again minus cosine. and we get another time the inner derivative. So in this case, we would get here for the second order time derivative minus E0 times cosine, and this whole argument, and then from the inner derivatives, we get an omega square. And then from here, from the Laplace operator, we would basically get also E0 minus cosine, and then from the inner derivative, we would get a k square. So, and that, as you can see, omega and k are related to c, and so they can cancel out this term. So you can pause the video if you want and take a sheet of paper, calculate these derivatives, and then you see that this solution is indeed true. However, this is not the most general solution. The most general solution would be to consider an exponential function with an imaginary argument. So once again, if you have never heard about imaginary arguments or complex numbers, that's no problem, because we will also discuss this in the mathematical tutorial. So don't worry, the important thing here is that you realize that you can express e to the I something like a cosine function and a sine function. So that's basically just a different way of writing it down. Okay, so that's a bit of an excursus here into what is called electrodynamics. And this is the theory that was considered mostly before quantum mechanics. So this is here basically the status quo before quantum mechanics was developed. So let's continue this excursion a bit more. So what we have seen is that the general solution based on these Maxwell's equations here is such an expression E0 times an exponential function with an imaginary argument. And now we can select several, or we have several choices for this E0 vector here. And depending on what it looks like, we can get several different polarizations for our electromagnetic wave, so for our light. For example, we can get a linear polarization where you can see the electric field is just such a sinusoidal wave. Or we could also get such a circular polarization where it wraps around in a sphere or in a circle. So we get then such a spiral trajectory over time. So if you find this really interesting, and if you want to learn more about the polarizations of light and also about these Maxwell equations, then please have a look at my other course here on this website, where I consider electrodynamics based on the Maxwell equations. You can see this course is also 10 hours long, so of course there's a whole lot more about this than just these two images and this brief discussion here. So in this course we will also deal with magnetostatics, electrostatics, and then also time-dependent problems. Okay, so now that is enough with the excursion and enough of the advertisement. So that was one part of the knowledge that was known before quantum mechanics has been developed. This was that light is a wave. And in the next lecture, we want to discuss the other side. We want to discuss the particle-like properties of light. So stay tuned, and I hope I see you in the next lecture. Welcome back. In this lecture, we will ask again, what is light? But this time, is it a particle? Coming back to the last lecture, we have learned that light has wave-like properties. So this means we can characterize light by an electric field and also a magnetic field, and both of them are expressed as cosine functions over the time and over the position vector. So what this means is that the energy that is transmitted by light is proportional to, or is characterized by, the amplitude E0. In fact, the intensity is proportional to E0 squared. Now, in the next experiment, the photoelectric effect, we will see that this cannot be accounted for by light as a wave. So the photoelectric effect works as follows. We have a piece of metal and we shine light to this metal. And as a consequence, the metal heats up and electrons are emitted. And so people really thought that the heating that takes some time just leads to the generation of electrons. But as it turns out, physics behind it is quite different. So an experiment that we can do is we can actually use a second piece of metal as a second contact and then apply these wires and measure the current that flows. So these emitted electrons here will have a kinetic energy. So they will have a velocity and a momentum p. And due to their kinetic energy, they will move from here to there and will generate a current. Now, the kinetic energy can only be measured in a very difficult way, so people decided to use a bit of a different experiment to make it a bit more simple. First of all, they put these electrons into a vacuum so that they can really move freely from the right side to the left side without any collisions. And also they applied a gate voltage to the second contact. And this voltage U generates an electric field, the charge of the electron times U. And when this energy that corresponds to this quantity is equal to the kinetic energy, then the electrons will not move at all. So basically this U generates an opposing electric field that cancels the electron flow, and therefore, if it is tuned correctly, will lead to a current that is zero. So the experiment goes like this: you apply the light and then you tune your voltage U until the current is zero. And then you know the energy E times U is exactly equal to the kinetic energy. So we have now a way to measure our kinetic energy indirectly by E times U if I is zero. Now, what people have done next is they have used light with a well-defined wavelength or frequency f. And they have changed the frequency. So for example, using some red light, using some green light, using some purple light. And now they have done this experiment where they have tuned the voltage U until the current is zero for different values of f. And then you can plot the U values. And what you can see is that below a certain frequency, you will not get a current flow whatever you do. So you don't have to apply any voltage. And the reason is that no electrons are emitted for these frequencies. But then there exists a critical frequency, this one here, above which the electrons are emitted. And when you keep on increasing the frequency, the required voltage increases linearly. So after performing the experiment, you can just continue this linear dependence here and see that, of course, this function will cross the U-axis. And you can write down such an expression. You have here basically U is equal to the frequency times the slope, which turns out to be the Planck constant. And you will have here a constant which we called V0 or W0. And when you repeat this experiment for different materials, for example silver and aluminum, you will see that the slope is always the same. And this is because the slope is determined by this Planck constant, which is a universal constant. However, this other constant, V0, this is material dependent. So it's different for silver and aluminum. Now it's also very important to realize that when people repeated this experiment for different light intensities, the result was always the same. So this means the result is independent of the intensity. And this is already saying that the light in this experiment cannot really be treated as a wave. Because if this was true, then the intensity would be proportional to E squared. And then the energy that is transmitted is basically given by E0. But it turns out the experiment says that this is here not the case. Also, the whole experiment was instantaneous. So before people came up with the actual interpretation of this experiment.